welcome to this class. In the last class, we have discussed so many problems from exercise 4.2 related to determinants, expansion of determinants. And you might have done some more problems. Once you try to solve some problems from the previous year question papers and all, definitely you will be facing some problem to how to apply this, which operation, which is the best one and all. Those things and all you note down and share, we will discuss in the next class. I told you already, in this class we are going to discuss some of the application of determinants. Like area, whatever you learned in lower classes, area concept already you have learned in class 11th. That one, as well as inverse of a matrix and how to make use of the inverse of a matrix for solving a system of linear equation. Now, first we will go to the concept area of a triangle with the vertices x1, y1, x2, y2 and x3, y3. In class 11th, in coordinate geometry, you have studied area of the triangle as, just try to recall that half into x1 into y2 minus y3 plus x2 into y3 minus y1 plus x3 into y1 minus y2. Now, how will we connect this concept with our knowledge of determinants? Let us see, it is the same only. I will tell you how it is. Delta is equal to half into x1, y1, 1. x1, y1 is the first coordinate and the second row x2, y2, it is the second coordinate, vertices I say, and the third row x3, y3, third one. So if three vertices is given, we can write delta is equal to, you just expand and see. Suppose you take the first column to expand, what will happen? You see x1 into y2 minus y3 minus x2 into, it comes, but it is y1 minus y3. Now we will make it as plus x2 into y3 minus y1, just interchanging. So this determinant expansion is definitely what you learned in class 11th. So this is one of the application. Concept is very simple. We can, if three vertices are given, you can find out the area of the triangle. And sometimes the question can be find the value of k if the area is 10 square meter. It can be like that. We will discuss some problems. Okay. Now see, suppose delta is equal to 0, what happens? If delta is equal to 0, that is there is no triangle at all. Right? That means if the 3 points are collinear, there will not be any triangle. So that the concept can be used. Show that the 3 points are collinear. So the delta will be 0. That is one of the concepts. Now see, so if 3 points are collinear, what happens? Delta is equal to 0. Now we will have a glance through the problems from exercise 4.3. See, find the area of the triangle with the vertices at the points given in each of the following. Now it is, as you know, it is very simple, only direct expansion of determinant. You can do yourselves. Show that the points are collinear. How will you show the points are collinear? Just you write delta is equal to half determinant x1, y1, 1, x2, y2, 1, x3, y3, 1. Substitute this point, expand it. If the determinant value is 0, the points are collinear. Now again I told you, find the value of k, third question. You can do it yourselves. Now fourth one, find the equation of the line joining. 2 points it is given, right? Only 2 points, 1, 2, that is 1, 2 and point 36. Using determinant, find the equation of the line joining. Here in the delta equation, delta is equal to what? The third row we will write xy1 because we will consider let p xy be any other point, a general point. So that delta is equal to half, first point 1, 2, second point 3, 6 and the third point, a general point pxy. So that delta is equal to this. This one direct expansion, or you can make those 1, 1, 0 as you like. Okay. Direct expansion will give you the answer y is equal to 2x. This is the equation of the line. So I am telling it is very simple one. Now let us move to the next one. That is for finding out the inverse of a matrix. Already I told you that is one of the application. Before going to inverse, we should know one after the other. First one, minor. Minor of an element of a determinant. Keep it in mind. Second thing, cofactor of the element of a determinant. Third one, matrix of cofactors. Fourth one, transpose of matrix of cofactors. Then adjoint A. Right? And already you learned determinant A. So using these concepts, we are going to define our inverse. Now see, what is meant by minor of an element of a determinant? Now, first consider a 2 by 2 determinant. Determinant A is equal to, determinant is a general one, A11, A12, A21, A22. Now, we are going to define minor of A11. What is minor of A11? It is determinant A22. Right? And determinant A22, it is A22. Now, what is this determinant A22? You know, minor of A11 while calculating, delete that row and column in which A11 lies. Deleting that, what will be the resulting one? It is determinant A22. So the answer is A22. Minor of A11 for a 2 by 2 determinant, it is A22. Now, next one, minor of A12. Minor of A12, I told you already, delete that row and column in which A12 lies. What remains? A21. So minor of A12 is A21. So you can tell what is the minor of A21? Good. It is A12. Then minor of A22, it is A11. Right? Now, minor of A22, all the four over. Next one it is, if it is a 3 by 3 determinant, how to calculate the minor? In the previous one it was 2 by 2 determinant. Now I have taken one example, determinant A11, A12, A13, A3 by 3 determinant. Now you just try to formulate this. What will be the minor of A11? You only can tell, okay, delete that row and column. A11 lies in first row and first column. So minor of A11, it is the resulting determinant, which is determinant A22, A23, A32, A33. It is a 2 by 2 determinant. When the determinant A is a 3 by 3 determinant, minor of each element will be a 2 by 2 determinant, 1 less, the order less by 1. So what will be minor of? That is, minor of A11 is denoted by M11. In general, minor of Aij is denoted by Mij. So here minor of M11, it is A22, A233 minus A32, A33, 23, determinant expansion. Then what will be minor of A12, which is M12, M12, delete column and row, the remaining A21, A23, A31, A33, and expansion will give you A21, A33 minus A31, A23. Now next, what is minor of A13, A13? Similarly, you can tell 9 minus will be there, 9 elements are there, and 9 minus will be there. So here I have taken M11, M13 and as well as M12. Similarly, you can frame all the minors. The next one I told you, it is cofactor. Is there any relation between minor and cofactor? Is it defined in terms of minor? Let us see. What is a cofactor? Here, minor of an element Aij is obtained by minor of an element Aij is obtained by deleting the row and column in which Aij lies. That is the resulting determinant. Right? So minor of Aij is denoted by Mij, and minor of an element. I told you already in the first case, for a 2 by 2 determinant minor, it was a single element. So generally we say minor of an element of a determinant of order n, where n is greater than or equal to 2, is a determinant of order n minus 1, 1 less than the order of the determinant. Right? It was so clear from the previous examples. Now the next is a cofactor. What's a cofactor? Cofactor of an element of a determinant is, in terms of minor, no, it is the signed minor. Cofactor of an element of a determinant is a signed minor. What is meant by signed minor? We have to see. I will tell you. It is, suppose cofactor of A11. signed minor negative 1 whole power 1 plus 1. Right? That is, the 1 represents the row and other second one represents the column. So, generally we say Aij, cofactor of A11 is denoted by capital A11. Cofactor of Aij, element Aij is denoted by capital Aij is equal to signed minor. It is actually Mij written, but in addition to Mij, negative 1 whole power I plus j. So clear from the definition. Now you can tell what will be A11. A11 will be minus 1 whole power 1 plus 1 M11. Then minus 1 whole power 1 plus 1, it is 1 plus 1 2, negative 1 whole square, and even number it's 1 only. So A11 will be M11. A12 1 plus 2 3, negative 1 whole power 3, which is equal to negative 1. So it will be negative A12. So M11 will be, so A11 will be M11 and A12 will be negative M12 and A21 will be negative M21. That is, just we are adding the negative 1 whole power I plus j. Depending upon I plus j, even or odd, it become positive or negative. Here also, if it is a 3 by 3 determinant, you will get 9 cofactors. Right? For each element, there is a cofactor. Now, A32, it is negative M32. Now, the next one, we are connecting this cofactor with the determinant. Right? Earlier, you have studied how to expand a determinant using the first row, second row, third row, first column, second column, third row. You can evaluate or expand a determinant using any of the rows or columns. Here now we are going to connect with the cofactor. Those things can be written as determinant A is equal to A11, an element, into its cofactor, plus A12 into its cofactor A12. Again, A plus A13, that is sum of the product of the element with the corresponding cofactors. It's new. Previously you have studied determinant A. Now after knowing cofactor, this is the thing. Now again, first one I have written A11, A12, A13, that is the first row is considered. Here in the second example, 1, 3, 2, 3, 3, 3, that is third column is taken into account for getting the determinant value. Then one more example, A31, A32 plus A32, A32 plus A33, A33. And then what happens? What I have considered, you see, A31, A32, A33 shows it is the third row. So this determinant expansion is using third row. Then no need to worry about this one. The corresponding cofactor 31, 31, 32, 32, 33, 33. Corresponding cofactor, it is multiplied and added. This is the determinant A, the new concept after learning cofactor. Next, one more thing you can observe. Other than this combination, sum of the elements multiplied with the cofactor, this gives you determinant A. In all other combination, the value will be 0. Let us see. It is A11, A21, A plus A12, A22 plus A13, A23 is equal to 0. All such combination, here 1, 1, it is not 1, 1. If it is 1, 2, this also 1, 2 for determinant A. Now all such a different combination, the value will be 0. Now 2, 3 combinations I have written here. All these values is equal to 0. That is, sum of inverse, it is sum of product of elements of a row or column with the corresponding cofactor is equal to determinant A, and otherwise it is 0 from the previous two. Okay. The next one, it is adjoint or adjugate of a matrix. Right? First we have those minus, then second cofactors. Now we are directly telling adjoint or adjugate of a matrix. How you see? Adjoint or adjugate of a matrix is defined as the transpose of matrix of cofactors. So once you get all the cofactors for a 3 by 3 determinant A11, A12, A13, or capital letters only, all these together, if you frame a determinant matrix, then transpose of that matrix. If C is the matrix of cofactors, C transpose is adjoint A. Okay. So first matrix of cofactors C is equal to, it is matrix of, what are the elements you see? It is all cofactors. Cofactors of element A11, all the cofactors it is written, so it is matrix of cofactors. Then what is adjoint A? It is transpose of matrix of cofactors, that is C transpose. A11, A12, A13 become the first column. Second row becomes second column, third row becomes third column. So this is the definition for adjoint A. Now we are going to the next concept, which is one of the theorem. If A be any given square matrix of order n, then E into adjoint A is equal to adjoint A, C A into A is equal to determinant A into I, where I is the identity matrix of order n. This is theorem. Proof is simple only. Actually, proof is not so important. Anyway, taking many problems are the giving a determinant or a matrix. Prove that A into adjoint A is equal to adjoint A into A is equal to determinant A into I. This is always true. It's a theorem. Now we will do some problems from that also, and we will verify it also. Second theorem. If A and B are non-singular matrices of the same order, then AB and B are also non-singular matrices of the same order. Now earlier in matrix we have studied non-singular matrix and singular matrix and non-singular matrix. You try to recall that one. Non-singular matrix if determinant A equal to not equal to 0. Singular matrix if determinant A equal to 0. That's all. So if A and B are non-singular matrix, definitely AB is a non-singular matrix and BA is a non-singular. That means determinant AB not equal to 0 and determinant BA not equal to 0. Simple concept and we can verify also. Next one, theorem 3. The determinant of the product of matrices is equal to the product of the respective determinant. From the sentence itself it is clear. Determinant of the product of matrices. If A and B are two matrices, determinant of AB equal to determinant A into determinant A. That means separate determinant you can multiply. That is determinant AB is equal to determinant A into determinant B, where A and B are square matrices of the same order. This also concept clear through problem examples we can verify it. If A is a square matrix of order n, then determinant of adjoint A is equal to determinant A whole power n minus 1. First you try this one, do the problem, and if you don't get, you just in the next class we will discuss. Okay? It is easy only, that is why I am telling you do some homework. Okay? Now let us see the next application of determinants and matrices, that is inverse of a square matrix. Before that, I will take some examples. Right? Now, we know in the case of set of real numbers or natural numbers and all, negative 2 is the additive inverse of positive 2 because once you add you will be getting the identity element for addition. That is A plus negative A is equal to 0 for every A belongs to R. So what we say here, A and negative A are additive inverse each other, or negative A is the additive inverse of A. Right? Same thing now consider the multiplication, operation multiplication on real numbers. If A and B are any two real numbers, if A into B is equal to 1, which is the multiplicative identity, we say B is the multiplicative inverse of A and A is the multiplicative inverse of B. And like that, what is the multiplicative inverse of A? It is 1 by A. So A into 1 by A equal to 1 for every A belongs to R. So what we say, A and 1 by A are multiplicative inverse each other. Otherwise we say A and B are multiplicative inverse each other if AB is equal to 1. That is A and 1 by A are multiplicative inverse each other. Now we will take some examples before going to the definition of the inverse. We will take some example. You see, A is equal to 3, 1, 5, 2 matrix and B is 2, negative 1, negative 5, 3. Here, if I find out AB, you see, 3 into 2 plus 1 into negative 5. 6 minus 5, 1, first element. 3, negative 3 plus 3, 0, second element 0. Now second row, first element. 5 into 2, 10, 5, 2 into negative 5, that is 10 plus negative 10 is equal to 0. 5 into negative 5 plus 6, once again 1. So you will be getting 1 0 0 1 matrix, that is I2. Here A into B is equal to I2. So what we can say, A is the multiplicative inverse of B and B is the multiplicative inverse of A, or simply we say A is the inverse of B and B is the inverse of A. Now another example we will take. That is, consider this example. A is equal to 2 matrices are given. Find out the product here also. 10 into 2, 20 minus 19, 1. 190 plus negative 190, 0. Negative 2 plus 2, 0. Negative 19 plus 21. So you are getting once again AB. BA also you try to find out. BA also will be I only in this example. So what happens? AB is equal to BA is equal to I. To what we can conclude? This is the definition for inverse, already we discussed. So it is A is the inverse of B and B is the inverse of A. Let us take one more example. It is 2 matrices, it is given P and Q. Here also I say just multiplication. It is AB is PQ is equal to I and QP also I. So P and Q are inverse each other. P is the inverse of Q, Q is the inverse of P. Now I am going to take all these three. I did not tell anything about those. In all the previous cases, we got AB is equal to BI is equal to I, XY is equal to YX is equal to I, and PQ is equal to QP is equal to I matrix of order 2. That is the identity matrix. Now let us see the speciality. I have selected one B in such a way. Here you see 3 opposite, diagonally opposite it is 2, that 2 is taken here. And diagonally opposite to 2 it is 3, that 3 is written there. Right. Here 1, here negative 1. A sign is changed, you see. Here 5, it is negative 5. Opposite sign it is kept for this and this one interchanged without changing the sign. This is the speciality. Now let us see the next one. Same thing we have to see in the next example. Here 10, diagonally opposite 10, it is 2, 2 is written here. Diagonally opposite to 2, it is 10, 10 is written there. Negative 19 become positive 19 without changing the number there, and here negative 1 become positive 1. You could see some speciality, you observe that thing, and later we will reach to some assumption. You say here third example, 6 diagonally opposite to 3, 3 here. 3 diagonally opposite 6, 6 is written. Negative 1, it is written there only, but with the change of sign. Here negative 17 become positive 17. Here also something is there. Here I have selected such matrices so that the product become I. That is why we could say they are the inverse each other. Now see this example. Here 10 opposite to it is 2, 2 is written. 2 opposite 10 is written. Negative 18 plus 18, negative 1, 1. In all these 1, 2, 3 examples, we got AB is equal to I. Second case also AB is equal to I, BA is equal to I, PQ is equal to QP is equal to I. But now we are going to observe. Same principle is adopted in the last example. I did not change the method. 10 opposite to 2 I explained already. Sign is changed. Now my question is, in this case, will we get I? Whether A and B are inverse each other or not. Right. Here itself you can check if you want. You see 10 into 2, 20, that is determined. Here 10 into 2, 20 minus 18. First number is 2. It is not a 1. Then 10 into 18, 180 plus negative 180. Of course, second number is 0. Third, negative 1, negative 2 plus 2. Second row, first number is 0. And the last one, negative 180 plus, negative 18 plus 20, which is equal to 2. So what we got, AB is not I, but something is there. It is 2 common, 2, 0, 0, 2. So it is 2I. In such case, we can't say A and B are inverse each other. Let us see that. A is equal to B is equal to, AB is equal to, BA is equal to 2I2. Now this 2 I am taking to along with the b, so that this 2 if I take along with the b, it will come b by 2 into a is equal to I2. So what is the inverse of a in that case? A inverse equal to half b, and same thing b inverse is equal to half a. In this example, it become half a inverse each other. They are not inverse each other, but even then we are getting some multiple of I2. Now let us see one more example, x and y. Here you see 4. Here it is written for 2. This 2 is written there. 1 become negative 1, 5 become negative 5. Same principle is adopted while selecting the matrix y. I am asking in this case whether xy is equal to I or not, or yx is equal to xy is equal to I or not. If xy is equal to I, yx is equal to I, we say x is the inverse of y and y is the inverse of x, that we are going to. Here so you just see 8 negative 5. 8 plus negative 5, 3. First number element is 3. Minus 4 plus 4. Second number in the first row is 0. Second row first element 10 minus 10, 0. Minus 5 plus 8, 3. So finally what we got, xy is equal to matrix 3, 0, 0, 3. That is 3 if you take outside, it is 3I2. Right? Concentrate there. In the previous example we got 2I2. Now we got 3I2. Same principle is adopted in all the examples. But we did not get in each case the inverse. Now we are going to correlate it. Here we can say x inverse is equal to 1 by 3y and y inverse is equal to 1 by 3x. Now we are going to form the definition for A inverse. Now see. This is the first example. In first example, in all previous example, if you observe, determinant A was 1. Right? Now, in this example, determinant A is 20 minus 18, which is 2. Now connect with the 2I2. Here, 20 minus 18. Determinant B, I no need to say now. Here, it is determinant A is equal to 2. We got 2I2 also, and half B was the inverse of A. Now in the second example, again see the determinant. That is 4 into 2, 8 minus 5, it is 3. Determinant value is 3. There we got xy is equal to 3I2. So something related with this determinant and this matrix. We are framing this matrix. Let us see. So, how to find the inverse of a square matrix? Already we got many examples how to frame for 2 by 2 determinant. We got all those examples, and when determinant is equal to 1, directly we got their inverse each other. Now, otherwise b by 2, b by 3 according to the determinant. How to find the inverse? That is the very important definition for A inverse, and this concept is also very easy. And in the examination point of view, you may get a 6-mark question from this or 4-mark question, right? Now, the definition it is A inverse is equal to adjoint A by determinant A. Now, you can recall those things, adjoint A or not, that you verify, okay? So, here you see determinant A is in the denominator. Here, determinant A should not be 0, right? If determinant A is 0, this A inverse we say not defined. We know division by 0 is not defined. So A inverse is not defined if determinant A is equal to 0. I told you already, a matrix A is said to be singular if determinant A is equal to 0. Non-singular if determinant A is a non-zero number. Here determinant A non-zero number means that's the condition. So what is the condition? A must be a non-singular matrix. A inverse exists only if A is a non-singular matrix. Now let us see that. So a square matrix A is said to be singular. Already you studied just for recording if determinant A is equal to 0. Singular for determinant A equal to 0. Non-singular for determinant A is equal to non-singular. Not equal to 0. Determinant A not equal to 0. Now, thus what we conclude? A square matrix A is invertible if and only if A is non-singular. Right? Now let us see. We will take one example. if A is equal to matrix, a 3 by 3 matrix is given, find A inverse, verify A into A inverse is equal to A inverse into A is equal to I3. Now recall those things till you get adjoint A. For getting adjoint A, you have to calculate cofactor, then matrix of cofactor, then transpose of matrix of cofactor, and the first step it is calculation of determinant A. Now what is determinant A? You know how to calculate determinant A, right? Determinant A is equal to, first if we along with the first row, if we expand 1 into 20 minus 3, 17, that is 1 into determinant of I3. Next, minus 4 into determinant 2, 3, 2, 4. Then next one it is 0 plus 0 into, delete that row and column, 2, 5, 2, 1. So the calculation comes as the first determinant value is 17, here it is 8 minus 8 plus 0 into it is already 0 only. So what is 17 minus 8? It is equal to 9. So first we got a determinant value, determinant A is equal to 9, because we know A inverse is equal to adjoint A by determinant A. Now the next one, we have to find out the cofactor of each element. Already thoroughly we discussed how to find out the cofactor, and A inverse is equal to adjoint A by determinant A. And what is this Aij cofactor? Once again recall that it is negative 1 whole power I plus j mij. What is this mij once again? It is minor of Aij. You know how to calculate mij. So directly we are going to calculate A inverse. For each one, we have to assign the sign for getting cofactor. At a time, we have to take the transpose also. So here for 1, what is the cofactor of 1? It is 20 minus 3, 17. It will be the same numbers, not negative 17. First A1, 1. So it is 17. Then second, for next one, it is for cofactor of 4 is A1 plus 2, it will come negative 1 whole power 1 plus 2, it is negative only. That sign also we have to consider. 8 minus 6, 2 with the negative sign, negative 2, and it is not written there. It is written here. Why? We are taking the transpose also for getting adjoint A, right? So for each cofactor, we are writing the opposite to that for getting the transpose, and for cofactor we are assigning the sign with the minor. So this way we can find out. Now what is here? Now what is this adjoint A by determinant A? We got a determinant A is equal to 9. Here what you can do, whether your answer is right or not, you will just verify A into A inverse and A inverse into A. If it is I3, we say this is the inverse. Very easy for verification. Now we will go to exercise 4.4. That is only application of determinants with the inverse of a matrix. How to calculate inverse of the matrix and how to apply for solving the system of linear equation. In the next class, we will discuss all these things, right? Okay, before that, before coming to the next class, you have to do maximum problems from expansion of determinant as well as calculating in with thorough with the each time we won't write C1, A11, A12, A13. Directly we will write the adjoint A, right? So that be familiar with how to find out A inverse as well as the expansion of determinant, and we will go directly to the problems. Okay, thank you.